That was relatively easy. You should have seen trying to schedule freshman labs. Oh my gosh. Questions about Lab 1? I know there's questions about Lab 1 because I just heard a bunch. Who'd like to ask a question about Lab 1? Yes?
I've been noticing like slight jittering on one side. It's very subtle in terms of what the pattern is, but it seems to me like that would be something with the timing, but on the VGA side, which is largely something that we didn't write. Okay. Do you know, is there a way that we should go about solving that? Is there something about, or?
Okay, so slight jitter on the raster has a couple of possible different causes. Are you using the improved VGA driver or the original? The improved. It turns out that you can change one line of code and that goes away. I see some of you are nodding, you've had this happen. You change it to something else slightly different, it comes back. And what's happening is that the place and route section of the compiler is optimizing differently every time you compile the code and is moving the VGA controller a little further from the connector or a little closer to the connector, or a little further from the memory or a little closer to the memory. And I don't know of any way to control that. Has anybody messed with the layout controls? They tried to, I mean, you don't want to do manual place, but you can modify the way that the placing is done. In fact, since place and route is NP hard, right? It's a NP hard problem. Every time you hit compile, it actually throws the dice and chooses another way of placing the hardware on the FPGA, so that you can not even change the code, but just recompile, and the flicker will go away. Sometimes. It's very disturbing. I'm not going to worry about it. Minor quivering. I mean, if the raster is tearing and ripping back and forth, sure, that's a bug. A little bit of flicker in the corner of the raster, I'm not going to worry about. Since it seems to be non-deterministic. There's no way to debug it. What other questions? Anything about M4K blocks? Everybody got code? Okay, how many people can have a state machine displaying on the screen? Most people, or at least half. Okay, good. I will be in lab tomorrow afternoon. I have another class in there tomorrow afternoon, and so I have to pay attention mostly to that class, but I'll probably have some time to answer questions tomorrow afternoon. This is Wednesday. I have a lecture this afternoon at 2:55. I could come into lab for a little while before that. In general, starting next week, the 2300 lab will be in the lab Monday, Tuesday, and Wednesday from 1:30 to 4:30. And you cannot go in there during that time unless you ask the TA first. If the TA says it's okay, you can sit down. If the TA says it's not okay, you leave. So at this point, given that half the people have the state machine running, and probably everybody has stared at the code for hours at this point, is there any real reason for me to step through the other 150 lines of code? I don't see any particular reason, so I'll be happy to answer questions about the code. Be happy to answer questions about the code, about how it works, about the state machine, about M4K blocks. But if there's no questions, I'm going to move on. Very quiet. Did I hear a possible question down here?
The question was like the setting of the rule, right? I have just used a zero initial rule. So I have used like switch 0 for changing the rule. Is it like, I think the instruction says switch, some particular switch 7 or something needs to be used. 17.
To enter the initial.
So the
Would it be okay if I just use switch 0?
so there's 4 push buttons, and then there's 17 switches, right? Do you mean push button 0? That's fine. The one thing is that you enter the rule on the first 7 switches, right? And the rule can only affect the calculation when you press reset. So you have to copy those switches at reset time into a separate register. Okay, that's the one thing you do have to do. So you can't be in the situation that you fill the first screen, you change the rule, you say update to the next screen and the rule changes. That's not allowed. It can only happen at reset time. Any other questions? Yeah.
Could you talk a little bit more about the timing information of the M4K block?
Timing of M4K blocks. All right. So M4K blocks have registered address and data so on the clock edge, if you specify an address register value in your design of A prime or D prime, or A prime and D prime, address and data, then on the next clock edge, those are loaded, those become available to the M4K block. 1 clock cycle after that, the data appears at the output of the M4K block, unless you have asked for the output to be registered, in which case there is yet another cycle before it is available. So 2 cycles after you ask for data, you can read the data here. On a write, you have to set up, the setup time is finite for address and data before the write enable goes, what is it? It's write enable high. Yeah. So before write enable goes high, this address and this data have to be valid. That means in a clock system that you have to load the address prime and the data prime 1 cycle before you raise the write enable. So the data and address have to be stable for 1 cycle so that they're on these buses before you raise the write enable. Otherwise, you will write some other address than you think. Now, all this can be pipelined. So you can do an average of 1 read per cycle, but you have to delay the interpretation of the output 2 cycles from when you set the address. So you can set address 1, address 2, address 3, address 4, and then read result 1, result 2, result 3. So after you fill the pipeline for 2 cycles, you can get 1 readout for every address you put in on every cycle. I don't think that was my phone. Is that enough on M4K blocks? Yeah, okay. Yes? So then what you're asking is, how do you randomize the seed for the random number generator? Any ideas? Perfect. Right. So if you have the seed changing at 50 megahertz, then the time you push the button relative to the seed is essentially a random value. And that will randomize the seed and give you a different random number sequence every time. That's the best way of using the human as a random number generator. In fact, that's the only way I can think of to do it. Unless you unless you take the seed from, say, the time of day clock, which you would have to build.
Where is the VGA clock source? Where does this signal come from?
VGA source is derived from the 27 megahertz input by way of a phase lock loop. So there are 4 phase lock loops on the chip. Are you familiar with what a phase lock loop is? Yes, no? Okay. Let's talk about phase lock loops for a minute. So a phase lock loop is a device that has a phase comparator, XOR, or a multiplier, either one. If it's digital, it's XOR. If it's analog, it's a multiplier. Followed by a low-pass filter, followed by a numerically controlled oscillator, if it's digital, or a voltage-controlled oscillator if it's analog. And the numerically controlled oscillator is then fed back and compared. So if we were to do this, if we were to have some frequency input here and some frequency feedback here, so this is F out, then if we match the phases of this, if we set the phase difference to 0, then F out would exactly match F in. However, what would happen if we put a divide by n, digital divide by n there? Then F out is going to be, for constant phase, F out must be n times F in. And so we have a frequency multiplier. But what if we did this? What if we put another division factor m here? And dividing frequencies is easy, right? It's just a counter. Then we have the interesting relationship that F out is equal to F in times n divided by m. And so, depending on the depth of the counters, how many bits of each of these you are saving, you can make any rational frequency, any rational valued frequency based on a given input. So 27 megahertz is F in. If we pick N and M correctly, we can get approximately 25.175 megahertz output, which is the VGA clock frequency. Now, I'm not sure how many bits that the on-chip phase lock loops, I just can't remember. I looked it up, but I can't remember. But I think it's on the order of 5 and 4, or 6 and 4. It's what? It's what?
14 by 15.
14 by 15? Wow! 14 bits here and 15 bits here?
Value of 14 there and value of 15.
Oh, okay, so it's 4 bits each. Okay, so it's 4 bits each. So you can make any rational fraction that is limited to any integer value up to 15 over 15.
But that will give you 25.2. Would that,
Close enough.
does it make any difference in the jitter?
Oh, that's interesting, because on an old style analog tube, the answer is no. But on a new style digital LCD, yes, possibly. Yes, possibly. Interesting. So the way that phase lock loops are used on this particular chip, they are used to make one frequency into several other frequencies. I've played with it a little bit. You can take the 50 megahertz signal and you can clock it up above 200 megahertz, and M4K blocks still work. Some other circuitry fails before that, depending on what you build. Oh yes, there's also a phase changer in maybe both places that allows you to change the phase by a constant amount, so that if you want the phase of one signal to be 90 degrees above, in front of the phase of another signal, you can do that. And that'll be handy when building the Nios 2. Somebody told me this should be pronounced Neos 2. I don't know. Nios 2 CPU. It turns out that the clock signal for the Nios has to be delayed 3 nanoseconds from the clock for the SD-RAM. And the phase lock loops do that for you, so you don't have to do that yourself in some weird set of delay hardware. What else? Is that a question? Oh, that was just sort of a, well, it's kind of one of these things. All right. Every once in a while, if you build a really big circuit on the FPGA and you're using a couple of different phase lock loops for different frequencies of different sections, you may get weird errors at synthesis time to the effect of clock domain doesn't reach circuitry, or some weird thing like that. And that's because each phase lock loop has its own distribution tree, clock distribution tree, but they don't all cover the entire chip. You might see that later, you might not. I've only seen it once. What else about Lab 1? It's to change the frequency, and since it's phase locked to the input, it keeps it constant. Yes.
Like, supposing I'm not using it as a clock device, I'm not using the devices and multiplying the frequency, then it's to basically make sure that my frequency, my output is the same as the input all the time. And it gives a feedback to the
Yes, and depending on how the phase lock loop is implemented, the output may be more regular than the input. It may do a little bit of filtering to keep the jitter down on the output. You're quite right on that. I don't know how this phase lock loop is implemented to know how good the jitter reduction is. Anything else? Well, let's talk about Lab 2, since it's coming right up, starting next week. Which means really, since every lab is 2 weeks long, it actually starts Saturday morning. All right. So that you get the full 2 weeks in. And what I'm going to ask you to do for Lab 2 is to take data out of the audio codec. The audio codec has a bunch of features we'll talk about in a minute. But one of the things it can do is to digitize analog signals, audio signals coming in. I'm going to ask you to take the left and right channel out of the audio codec, feed these each into a CPU that you're going to build. And each of the CPUs is going to have a program running which will be a digital filter. So each of the CPUs will be running DSP code. Then we'll loop the output of the CPU back into the audio codec to be put out to the real world. So there's going to be left and right channels in and left and right channels out. And we're going to loop these back out through the codec. So this is really kind of embarrassingly parallel computing. It's computing where we're going to use 2 CPUs. That's to get used to implementing multiple objects on the FPGA. They're going to be the same CPU, 2 instantiations, running their. Each one's going to be running a separate copy of the code. And one reason I am making a fairly simple lab here, conceptually simple lab, is that I've never had students actually use the particular CPU before that you're going to be using. And so you're being the test subjects. You're being the guinea pigs here. And so I wanted to keep it a little bit simple until I watch what happened. Alex?
What exactly is a codec?
Codec. It's an encoder-decoder. It is a device that takes in analog and puts out a digital stream. And I'll go through the functions in some detail. It's a monster chip. It's got all kinds of stuff in it. So we need to talk about, for Lab 2, we need to talk about DSP. How many people have done anything with DSP at one point or another? All right, how many people know what's referred to as direct form type 2? Okay. So we need to talk a little bit about DSP. We need to talk about the CPU a little bit, since it's probably a type you've never seen before. It's a stack CPU running a stack compiler. And so it's, has anybody ever programmed in a stack language? Forth? Any stack language like that? By the way, I need a name for the stack language, so if anybody can come up with a cute name, that's good. I'll attribute the name to you and put it on the website. The only constraint is that it has to be PG. Right? I mean, it can't be a rude name. And lastly, we need to talk about the codec itself, which is a piece of work. So this is hardware. Audio codec is a separate chip on the DE2. It is a Wolfson WM8731. codec, and we need to talk about that. So where do you want to start? Well, let's start with CPU. There's going to be, well, let me, before I do that, say that you're going to write DSP code as software running on the CPU. You're going to be interfacing with a thoracic written driver which communicates with the audio codec. There's actually two kinds of communication with the audio codec. So there's a codec driver, which I haven't drawn. Codec driver, which is going to do the setup for the codec. It's going to say, what should the left channel volume be set to? What should the right channel volume be set to? What should the low pass filters for each channel be set to? Should the mic be turned on or off? Should either channel be muted? And a dozen other features of the codec. Then there's also going to be the high-speed digital audio channel, which blasts data at 48 kilohertz between the CPU. I think it's actually, there's a mistake in the code, it's actually 47.5 kilohertz between the CPU and the audio codec. And from your point of view, when you're writing this data, it looks like 16-bit fixed point 2's complement. So the 2's complement 1, so 2's complement 1 would be what? 2's complement 1, 16-bit 2's comp. A1 is value FFF, 7FFF, right? That would correspond to plus 1 volt at the output, and FFF would correspond to minus 1 volt. So it's 16-bit 2's complement. Now, inside this driver, or inside the interface that you don't have to write, your data is going to be serialized and blasted out of a serial port at a fairly high rate. 16 times 48 kilohertz, in fact. So we need to talk a little bit about that whole process. But I think let's start with the CPU. So you're going to want to start reading up on Lab 2 like soon. Stag machines are nice because they're small. And so you can expect to get lots of them on the FPGA if you're doing parallel processing, particularly fine-grained parallel processing, which you will have to do for Lab 3. So using this CPU might be a possibility for Lab 3. You don't have to use this CPU for Lab 3, but it might be a useful thing to do. But for Lab 2, you do have to use it. So there's going to be a state register which you don't have access to. It's not part of the programmer's model. There's a program counter which you will have access to as part of the programmer's model. There's an I/O buffer which in the implementation you're going to be using is 8-channel. And there is a stack. And there will be two outputs from the stack, one called top and another called next. Which go to the ALU. and which actually doesn't go here, it goes to the data bus. One of which data bus is ported into the stack. And also top comes out directly onto the data bus. There's an address bus, which of course has access to the program counter, but the program counter also has access to the data bus because we want to be able to set it from software. Otherwise, we can't do function calls. Now, there's also going to be some memory. This is not stack memory. It's actually RAM. And this is, of course, driven from the address bus and bidirectionally onto the data bus. And the I/O buffer is driven from the data bus. So that's all there is. The stack you can choose the size of. Can be any size you want, but the two sizes I was using is either 18 bits by 8 words or 18 by 16 words. RAM is for a maximum of 4096 words, max. You get to choose the size of memory depending on the size of the program and the data you need, but it can't be bigger than 4096 words. That's all there is. There are no named registers. There is nothing you ever do in the code that requires a register name or number. Every operation is a stack operation. You do, of course, require some memory addresses, but never a register name. It turns out that people have a fair amount of trouble writing code for a machine like this. So the compiler hides some of the details from you because otherwise it's just too ugly for words. The machine language, the kind of instructions that are issued on a machine like this tend to be things like push immediate, and then an integer, and an integer here means a 12-bit 2's complement number, which is sign extended into 18 bits. You can do a push with some address, push A, which does this operation. Mem of address A gets the value that's on the top of the stack. So you specify the address, and top of stack is copied into that address. So it's actually moved to that address. Pop A takes the value of top and moves it to mem of address A. Jump A puts the value of A into the program counter. And JZA says if top is equal to 0, then A goes to the PC. And there's a jump not 0 also, which does what you'd expect. A load indirect, which allows you to do, an LD allows you to do a mem of top goes to top, and a store in which the top of stack goes into mem of the next value on the stack. And there's a push PC and a pop PC. So the program counter goes to top, and top goes to program counter. An in of n and an out of n, which takes the input of I/O channel n and puts it in top, or it takes top and outputs it to output channel n. And then there's a whole bunch of binary operators like add, subtract, multiply, bit and, logical and, shift left, all of which use the next and top of stack and store back to top of stack. So for instance, add takes next plus top and stores it back to top. The one weird instruction that I'm going to probably ask you to hack, I defined a multiply. I defined a multiply in 10.8 notation. So the multiply is originally defined. By the way, this particular architecture that I used was modified from a GPL version available at Hiroshima University. Reading the documentation was interesting, since it was in Japanese. So luckily the Verilog was in English. But Google Translate did a good enough job to kind of figure out what was going on. So I took the basic structure and I added a few instructions to it, which made it more flexible and nicer. And I changed the multiply from an integer multiply to a 10.8. 10.8 here means that we're using 18-bit fixed point, 18-bit 2's complement fixed point. So 18 bits with the binary point after bit 7. And this is the sign bit. Bit 17 is the sign bit, 18 bits total. Bit 7 is the highest order fraction. Bit 8 is the lowest order integer bit. So the multiply takes two 10.8 numbers and returns a 10.8 number. This is useful for doing DSP, where we're going to find that many of the numbers that you need to deal with are fractional. In fact, some are very small fractions. In fact, probably what you're going to have to do with this processor, the single change you're going to have to make to the processor, probably to make this lab work for you is to change this multiply from 10.8 format to 2.16 format, or maybe 4.12 format, so that you have more bits of fraction and less of integer. And we'll see why when we do the DSP stuff, but you will probably want to modify this multiply instruction. It's not a lot of work to do that. Yeah, whenever somebody says that, you know, it should only take you an hour, you say, 6 hours. I hope it doesn't take 6 hours. Any questions? Oh, did I? 414. Sorry, yeah, 414. Now, I don't know how many of you messed with compilers, but one of the things that compilers tend to do is to take a high-level language and convert it into a stack format, so that because it's easy to then build a machine that's a stack machine. And so the fact that compilers do that suggests that humans are not awesomely good at using stack machines. Any of you ever programmed a Hewlett-Packard calculator in reverse Polish notation? That's obsolete now. You got to kind of turn your brain inside out to do stack calculations. But the compiler I wrote for this is a very minimal compiler, which means it takes a stack language input and puts out a stack assembler. So you are going to have to turn your brain halfway inside out to use it. I wrote an assembler. You can write it all in assembler. You can write the code in assembler. Nice thing about DSP is that the operations are rather regular. There's not going to be a whole lot of branching. There's not going to be a whole lot of complicated selection, but there's going to be a lot of arithmetic. I think rather than start in the last 5 minutes talking about compiler, again, I'll ask for questions with regard to Lab 1, Lab 2, or anything else in the course. Somebody said they had a problem getting Signal Tap to run. Anybody had a problem with Signal Tap? Anybody use Signal Tap? Work for you? You had a problem? What was the problem?
It was saying the instance not found.
Ah, in the hideous instance. Well, all right. So now, by instance, did it mean a register name, or did it a state? It turns out that Quartus 2 scans your code and notices that you're using a signal, multi-bit signal, as a state variable. And it doesn't actually build a register, but rather it abstracts that away into a sequential one-hot control line. So the register doesn't actually exist anymore unless you tell Quartus to keep the register. There's some way, I think, in Signal Tap to do that, but I know that you can put there's a synthesis attribute keep. Has anybody looked that up yet? You can Google up Quartus synthesis attribute keep, and you'll find out how to do it. And then the register won't be abstracted away. The implementation won't be quite as compact, but who cares if you can debug it? So that's what you have to do. Did you try that?
Actually, I tried recompiling it again. I restarted the signal tap analyzer, and it kind of worked later on.
It kind of worked. You mean, what did you do when you recompiled? Did you ask to keep the register, or did you use a signal tap option to...
Use the pre-analyzer option.
Pre-analyze, okay, yes. So yeah, signal tap can look at, you can specify pre-analysis or post-analysis registers, and the post-analysis registers won't include state variables, but the pre-analysis registers should. And so if you specify that, that should force a keep. So exactly one person has used signal tap? John, you've used it too? It worked for you? Is it used?
Same problem, but actually when you recompile it, it asks if you want to change the mode to pre-synthesis or post-fitting. If you make it pre-synthesis,
Then everything's there. And did you find signal tap useful for debugging?
I would not have been able to complete it with a signal tap.
Not being able to do what?
I would not have been able to complete it.
Without signal tap. Okay, so you found some logical errors that way, timing errors and so on. Okay, so that's an endorsement. The one thing about the real-time systems that we're doing is that simulation doesn't work very well because you can't simulate the VGA subsystem. You can't simulate the monitor, so you can't see the result. So signal tap is a viable alternative to simulation because it allows you to look at the internal state of all the variables. I tend to do very simple things. I tend to use lots of LEDs and watch it step through states. But if it's stepping fast, it's hard to see. You gotta blink real fast. Anything else? Let's get out of here.